In this video, we're going to finish up Chapter 7, Section 3, Multivariable Linear Systems. And the book says here, for a system of linear equations, one of the following will be true. There is only exactly one solution, there are infinitely many solutions, or there are no solutions at all. You might remember this when we did linear systems. If I have two lines, maybe the lines intersect at one point, there would be one solution. Maybe the lines are parallel to each other. They're never going to intersect, so there would be no solutions. Or maybe this blue line is covered up by the red line, and that means there would be infinitely many solutions. What we're going to do is the same here, but instead of lines, we're talking about planes. So here we might have one solution that would be a single point. That is where these three planes intersect at that single point. It's also possible we might have the solutions being a line. There would be a bunch of points there. Maybe the solution is all three planes are actually the same plane, so that would be infinitely many solutions. We might have no intersections. Here, two planes intersect at different spots, but there is no place where all three come together at one intersection. Or we might have all the planes are parallel and there are no intersections between any of them. So let's start digging into these possibilities. Here in example 4, they sort of spoil the surprise. Up here after example 4, it says an inconsistent system. So that means in the end, we will have no solutions. So I'm going to label these equation 1, 2, 3. And I'm going to start out my usual thing. I'm going to want to eliminate the x variable. So if I look at equation 1, there's an x. If I look at equation 2, there's a positive 2x. So I'm going to take equation 1 and I'm going to distribute a negative 2. So equation 1, I'm going to switch all the signs and double all the coefficients. So it's going to look like this, negative 2x plus 6y minus 2z equals negative 2. And I'm going to add that to equation number 2. So I'm just going to copy equation 2 right here below. And if I add these equations together, I would get 0x 5y minus 4z, z is equal to 0. I'm going to call this equation 4. And I'm going to put 4 down here for safekeeping. Now I'm going to use equations 2 and 3. Or no, I'm going to use 1 and 3. Excuse me, 1 and 3. Equation 1 has a positive x. Equation 3 has a positive x. So I'm going to run a negative 1 through the top equation. So negative 1 times equation 1. So that'll be negative x plus 3y minus z equals negative 1. And then I'm going to write equation 3 right under that. X plus 2y minus 3z equals negative 1. And I'm going to add the columns. X's cancel. And if I add the y's, I've got 5 of them. Add the z's, I've got negative 4 of those. And negative 1 and negative 1 add up to negative 2. I'm going to call this equation 5. Now, we could look at these, and if we think it through, we're going to see the inconsistency. So each equation is 5y minus 4z in blue, 5y minus 4z in black. The top one is equal to negative 2, and the bottom one is equal to 0. So how could the same things here add or subtract to different things here? But let's take this one step farther. I'm going to take equation 5, and I'm going to do a negative 1 times equation 5. So I'm going to copy this and just flip all the signs. Minus 5y plus 4z is equal to positive 2. And I'm going to put equation 4 right underneath it. 5y minus 4z is equal to 0. Now if I add equations 4 and 5, the 5y and negative 5y cancel. That turns into a 0. 4z and negative 4z turn into a 0. And on the other side of equals, 2 plus 0 is 2. So here's our inconsistency. 0 does not equal 2. There's no variables attached. This right here alone is enough to tell us there is no solution. This is an inconsistent system. There are no values of x, y, and z that would make all of these equations true. So if I bought back to here, yesterday in the video, the day one, we saw all the one solution videos. We just saw in the last example a no solution system. So my gut is telling me our next system will have the infinitely many solutions. So here are our equations, and let's see what's the best way to start this. I'm going to add 1 and 3, because if I look at the x's, right now I have an x and a negative x. So I don't have to do anything to them except add them together. So I'm going to call this equation 4. This plus this will equal 0. Y plus 2y is 3y. And then I have a minus 3z and nothing, so that'll be a minus 3z. And let me get this out of there for now. And then this negative 1 and this positive 1 are going to add up to a 0. So I'm going to call that equation 4. And now if we go back up to our top 3 original equations, I'm going to do negative 3 times equation 2. So I'm going to underline equation 2 here in red, and I'm going to distribute a negative 3. So that's going to be negative 3y plus 3z is equal to 0. I'll call this equation 5. Now, if I add these equations together, equation 4 plus equation 5, the y's would add up to a 0. The z's would also cancel each other out and become a 0. And when I add the 0 and the 0, I get 0. So here, if I back up here, remember this one, we got to the solution 2 is equal to 0. And that made sense, or that made no sense, so this was an inconsistent system. Now we've got 0 equals 0. Or maybe in another example, you would see 2 is equal to 2, or 5 is equal to 5. This is always true, so we have infinitely many solutions. Now, there is a way we can write this as an expression for infinitely many solutions. So let's see. If I come back up here, this one's pretty easy because I'm just going to concentrate on this. Y minus z is equal to 0. That tells me if I add z to both sides, y and z are the same number. So we've been using x's and y's and z's to express these infinitely many answers. We're going to let one of these equal a new variable a. So let's just let z equal a, and that means that y is also equal to a. So all we've got to do is figure out x now. We've got y, we've got z. So let's go back to the equation number 1. And equation number 1, I'm just going to copy it right here. X plus y minus 3z is equal to negative 1. Well, we figured out y, we could just replace that with an a. Z can also be replaced with an a, so this will become minus 3a. So we get x plus a minus 3a equals negative 1. So let's solve this and keep the x alone. Get over there. So we've got x, a minus 3a would be negative 2a. X minus 2a equals negative 1. And if we get the x alone, x will equal negative 1 plus 2a, or I'd write it better as 2a minus 1. So this is our x equals. So if I wanted to write my solution as an ordered triple, which is usually x, y, z, in this case, the x will be 2a minus 1, the y will be equal to a, and the z will also be equal to a. So now what this shows us is we can have infinitely many solutions. I could let a equal 1. If a is 1, this would also be a 1, and 2 times 1 minus 1 is also a 1. So this solution would work in all of the original equations. I could let, oops, didn't mean to do that. I could let a equal 2. So that means the next one would be 2, and then 2 times 2 minus 1 is 3. I would have 3, 2, 2 would also be a solution. I could do this forever. I could let my z value, my a, be 100. My y value would also be 100, and my x would be 2 times 100 minus 1, 199. So this would also work in the system. So there are infinitely many solutions. So up next, we've got a couple of checkpoints. These should mirror the examples we just saw. So I'm going to move this one down here for now so I have room. I'm going to label this equation 1, 2, 3. Of course, you should pause the video and try this on your own. And my idea here is I'm going to eliminate from using 1 and 2. I'll eliminate the x's. And then I'll do 1 and 3 and eliminate the x's and get 2 new equations. So let's see. I'm going to do negative 3 times equation 1. So I'm going to distribute a negative 3. That'll be negative 3x minus 3y plus 6z equals negative 9. And right under that, I'm going to just copy equation 2. 3x minus 2y plus 4z is equal to 1. And I will add those equations together and get minus 5y plus 10z equals negative 8. I'm going to call this equation 4. Okay, so I used 1 and 2 to eliminate x. Now I'm going to use 1 and 3. So to eliminate x, I'm going to need to take equation 1 and distribute a negative 2. Negative 2x minus 2y plus 4z equals negative 6. Right under that, I'm going to copy equation 3. 2x minus 3y plus 6z equals positive 8. And if I add, the x's are gone. I have a minus 5y and a plus 10z, and that's equal to positive 2. I'm going to call this equation 5. So I've got 2 new equations with x's gone. Now it's just y's and z's. So I'll move this one here. And I'll put this one right underneath it. Now let's see, I'm going to take equation 4 and distribute a negative 1. So in equation 4, all my signs will flip. This is now a plus, the 8 is a positive 8, and my middle term is now a minus 10z. So now if I add my columns, the y's are gone. Those cancel to 0. The z's also cancel to 0. So we get 0 equals, did I mess up a sign? Yeah, I think I misplaced a negative. I think that should still be a negative 8 after I distributed the negative 1. So if I add here, I get negative 6. So we can see this is not true. It's inconsistent. 0 does not equal negative 6. So this system has no solutions. All right, let's bring this one up. So let's see here. I'll just label these 1, 2, 3. And of course, I like to go after the x's first. So I'm going to do negative 2 times equation 1. I'll distribute a negative 2 across there. So there we go. And I'm going to add that to equation 2 as it is. 2x plus 3y plus z is equal to 5. And if I add those columns, x's are gone. We have a negative 1y and a plus 15z, and that's equal to positive 13. I'm going to call that equation 4. that right there. Now let's do -3 times equation 1. So again, I'm going to distribute a -3. And I'm going to add to that equation 3 as is. Equation 3 is 3x plus 7y minus 36z equals -25. So what are we going to get here? Positive, oops, that's supposed to be a y, not an x. We're going to have positive 1y minus 15z equals -13. And I'm going to call this equation 5. Ooh, bigger eraser, there we go. So this is equation 5. And as I slide it right underneath this one, I see the y and the negative y, so these are ready to add together right now. So the y's cancel to a 0, the z's cancel to a 0, so we get 0 is equal to 0. So these equations, we have infinitely many solutions. But again, we can express this in terms of a variable a. I'm going to back up here to this equation, and I'm going to get the y by itself. Y equals, we'll add 15z to both sides, so that'll be 15z minus 13. So we're just going to make an assumption here, and I'm going to let a equal z. So that's my, if I'm going to write up here my ordered triple x, y, z, I'll write it like this first, x, y, z. Well, we're going to let the z value now be called a. So I can hop right in here and change this to an a. Y is equal to 15a minus 13. So I'm going to come up here in my y spot and write 15a minus 13. So now I can go back to my original 3 systems. And I'm just going to go back to equation number 1 and plug in this stuff. So x we don't know yet. We're going to have plus 2 times y, but y is out, and we're going to replace that with 15a minus 13. And then we've got minus 7z. Well, we're going to replace z with a, and that's equal to -4. Oops, -4. So let's do a little distributing. 2 times 15a is 30a. 2 times -13 is minus 26. And then we've got a minus 7a equals -4. Let's combine like terms. 30a minus 7a will be 23a. And let's move this -26 to the other side, where it will become a positive 26. So this will equal 22. And to get x alone, we're going to minus the 23a. 22 minus 23a is our x value. If I had a little more room, let me slide this over. Oop, get over there. See if I have room. X coordinate is 22 minus 23 times a. So again, I could pick any number for a, 0, 1, 2, 3, a million, and just find the x and the y value in relation to that z value. So again, infinitely many solutions. Okay, one more example and one more practice problem, and here we go. Oh, a little history note. One of the most influential Chinese math books, blah, 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 published in 263 AD. Chapter 8 of the 9 chapter contains solutions of systems of linear equations such as this very system. So students have been solving these types of problems for almost 2,000 years. I'd like to get a copy of that very old math book. Non-square systems. So far, each system we looked at has been square. It means the number of equations is equal to the number of variables. 3 variables, we had 3 equations. If we had 4 equations, we'd need 4 variables. In a non-square system, the equation number differs from the number of variables. There is a neat little thing if you want to pause the video and read this. You know, these non-square systems pop up in GPS global positioning systems. So let's look at this non-square system here. Two equations, yet we have three variables. So let's start off as we usually do. I'm going to try to eliminate the x between these two systems. So I'm going to do negative 2 times equation 1. So there's negative 2 times equation 1. And I'm going to copy equation 2 right underneath it. And I'm going to add those together. So the x's cancel. I now have 3y minus 3z is equal to negative 3. Now we could leave it like that, but remember one of our things we can do with these systems is multiply or divide by the same number. Let's divide all of these by 3. So now we've got y minus z equals negative 1. Okay, this is right here is enough to finish this system off, so to speak. So I'm just going to get the y alone. Let's add z to both sides. So add z, we'll have z minus 1. Now let's see, I wonder if we could do this. That's x, y, z. We want our solution in that ordered triple. Right now, I could let z equal a. We're going to let z equal a. So in my ordered triple up here, I can replace the z with an a. So that means y, which was equal to z minus 1, will now equal a minus 1. So there's my y value, a minus 1. Now let's see if we can plug the y and z into our equation 1 and solve for x. So x was equal to, or x minus 2 times y, and our y value is now a minus 1, plus z, and z we're letting equal to a, and that's equal to 2. So let's get that x alone. Distribute the negative 2. We'll have x minus 2a plus 2 plus a is equal to positive 2. So let's combine some terms. We got a minus 2a and a plus a, so that's minus a plus 2 is equal to 2. If we subtract 2 from each side, we subtract this 2. 2 minus 2 is 0. And now we can just add a to both sides. So x minus a equals 0 becomes x is equal to a. So x is out, replace it with an a. So there's our representation of the numbers that would make this system work. Again, we would pick some number for a, and that would be our x and our z values, and the y value would be that number minus 1. All right, and that means if you can try this practice problem here, that'll be the end of the video. So pause the video and give this one a shot, and then fire the video back up and see how you did. Okay, now the way I approach this, notice in equation 2 there's only 2 variables. So if we set 4x minus z equal to 0, we could just move the z to the other side. Z is equal to 4x. And let's see, maybe right now we could do our substitution. I'm going to come up to this corner, x, y, and z. Well, since we've got this z by itself, let's let that equal a. So right now we know z is going to be replaced with an a. So that means 4x is equal to a. What would x equal? Divide both sides by 4. A over 4, or 1/4 a. So my x coordinate is 1/4 times a. So we've got z, we've got x. Let's go back to equation 1 here and solve for y. So I'm just going to copy it here. X minus y plus 4z is equal to 3. Well, we can replace x with 1/4 a minus y plus 4 times z. Well, z is equal to a, so that just becomes 4a is equal to 3. So let's combine our terms. We've got a 4a and a 1/4 a. That would be 4 and 1/4 a. I'm going to make that a mixed number. 17 over 4. 17 over 4a minus y equals 3. Again, we want to get the y by itself. So I think the quickest way to do that would be to add y to each side. So now y is over here, and we're going to subtract 3. So it looks like y is going to equal 17 over 4a minus 3. So if I had enough room, 17 over 4a minus 3 would go right in there. That's our new y value. I hope you got it. In class tomorrow, we're going to do some odd problems based on these, and there will be a few problems on WebAssign, and I'll see you then.
Thank you.